Hello, this is Dave Slopsma from Dimensional Consulting. Today I'm going to talk about how we can use simultaneous requirements to help us with our designs. A simultaneous requirement is when multiple feature control frames have the same datum references in the same order with the same modifiers. Here, the feature control frames that reference A primary and B at max material boundary secondary are simultaneous requirements. When multiple feature control frames are a simultaneous requirement, there is no datum feature shift between those features. We will see why that is and how we can use it to our advantage to accomplish our design goals. The 8 diameter holes are clearance holes for bolting the part to the mating part. As long as there is no critical clearance to nearby parts, it's typical to have big sloppy clearance holes for bolting the part to the mating part. It is also desirable to use those holes as datum features. When this part is assembled to the mating part, the surface A will constrain a translation in and out of the screen plus 2 rotations. The clearance holes, to gather as a pattern, will constrain the vertical and horizontal translations and the final rotation. Since this is how the part functions, we would like to reflect that functionality in our datum scheme. We establish surface A as our primary datum feature. We establish the pattern of clearance holes as our secondary datum feature. Now all 6 degrees of freedom are constrained. A tertiary datum feature is not necessary. Now let's focus on the 2 triangular shapes in the center of the part. They must be located tightly relative to each other. Their location relative to the datum holes is not critical. We control their sizes with profile of a surface all around. We control their locations with tolerance of position. Note the tight tolerances for size and position. For both of the triangular holes, we reference A primary and B at max material boundary secondary. They are a simultaneous requirement. To understand how our dimensioning scheme controls the triangular shapes tightly to each other and more loosely relative to the datum features, we look at the part sitting on the gauge for the triangular features. We will ignore the outside of the part for this example. That would be controlled by fitting between scribe lines on the gauge. Since the locations for the triangular features are specified MMC, we can use fixed size gauge pins in the triangular features. The size of the gauge pins in any direction will be their basic size minus the profile tolerance minus the position tolerance. Since the profile tolerance and the position tolerance are both small, there is little space between the triangular features and their gauge pins. These features fitting over their gauge pins is what will control the location of the triangular features relative to each other. But what about the datum feature shift? Since datum B is referenced MMB, datum feature shift is allowed. Remember that datum feature shift is the looseness between the datum features and their gauge pins. In the lower right corner of this slide, we see the calculation for MMB, which is the size of the gauge pins. The MMB is 7.4. If the datum holes are produced at size 8.1, we could have as much as 0.7 shift. But what does that mean for our triangular holes? There is indeed up to 0.7 datum feature shift between the triangular holes and the datum features, but not between the triangular holes relative to each other. Observe the datum features shifting relative to their gauge pins. This is datum feature shift. It affects the relative distance between the datum features and the triangular features, but it has no effect on the location of the triangular features relative to each other. This is how we can allow big sloppy clearance holes to the mating part, specify them as datum features MMB, and still maintain tight location of other features relative to each other. That's today's video. If you want to see more tips like this, please subscribe and visit my webpage at dimensionalconsulting.com.